The final way that we're going to find the delta H for a reaction is using something called standard heats of formation. Before we look at how to use standard heats of formation, we need to first look at the definition of standard heats of formation and understand that. The symbol for heats of formation is delta H naught F. Okay, delta H being the enthalpy. This naught symbol, or this little superscript of an O, means that the experiment is carried out at standard conditions, which means 25 degrees Celsius and 1 atmosphere. And the little F stands for formation. Now this is thermodynamic data, heats of formation. So you find the values for the standard heats of formation in your textbook. Okay, at the back of your textbook in the appendix, there is an extended list of compounds and their appropriate delta H naught Fs, which you may need to refer to. On page 253, there's a simplified list of some key compounds. Now, what these values are is the amount of heat that is absorbed or released when 1 mole of a compound is formed from its elements in their standard states. This is a very specific definition, and it's one that we need to evaluate wholly. Okay. A few important points here. We are forming 1 mole of the substance. It's going to be an exothermic or an endothermic reaction, and the element is formed the substance is formed from the elements in their standard states. And what we mean by that is it's formed from the elements in their regular state, so liquid, solid, gas, whether it's diatomic or not, at these conditions, at 25 degrees Celsius and 1 atmosphere. So if you look at these examples here, we've got H2 plus half O2 going to H2O, and this is a heat of formation. We're forming 1 mole of liquid water from its elements, so from hydrogen and oxygen in their standard states. So hydrogen being a gas and oxygen being a gas in its standard state. Now what you'll notice with these reactions is that we often need to use fractions because we cannot change the coefficient in front of the product. We're always forming 1 mole of the substance. It's very specific. The second one is another example of a heat of formation reaction, this time for carbon dioxide. It's formed from carbon and oxygen gas, and it's got a heat of formation. If we look on the chart, that is the value for the heat of formation. This third one, producing carbon dioxide from carbon monoxide and oxygen, is not a standard heat of formation. It doesn't follow the definition. Although we're forming 1 mole of the substance, we're not forming it from its elements in their standard states. A few things to note about this chart. There are lots of substances that have values of 0, and what you'll notice is that these are all elements. An element is not going to have a heat of formation because an element is already in its standard state, so it can't be formed from another element in its standard state. Another thing to notice is that the state, whether a substance is a gas or a liquid, so for example with water, the state matters, so we need to pay careful attention to that when we're recording values from the table. So there's a few things that we need to be able to do. We need to be able to write thermochemical equations for the standard heats of formation, and we need to be able to identify whether or not we've got an appropriate reaction. And then we also need to be able to calculate a delta H value for a given reaction. So first, we'll look at how to write out the reaction for the heat of formation of pure acetic acid. In the short table that I've given you, you're not going to find the value, but if you look in the appendix in your textbook, you'll find the value for the heat of formation of pure acetic acid, which is a liquid, is negative 487.0 kilojoules. When you're writing reactions for these, you're going to want to start from the product side because, by the definition, we're always forming 1 mole of that substance. In this case, our acetic acid is a liquid. The elements that we're going to use to form it are carbon, hydrogen, which is a gas and it's diatomic, and oxygen, which is a gas and it's diatomic. So you write out the elements, and then we need to balance this equation, keeping in mind we cannot change the coefficient in front of the product. So here we've got 2 carbons, we've got 3 hydrogens, and we need 1 oxygen. And there we have a balanced chemical equation, the thermochemical equation for the heat of formation of acetic acid. Now we can use the table values in order to calculate the delta H for a given reaction. And what we're going to do is first apply the formula that we're given, and then I'm going to show you why the formula is simply an application of Hess's law. If you've got a given reaction, some compound A plus some compound B, and it's reacting to form some compound C and some compound D, to find the heat of this reaction, what we're going to do is take the sum of the heats of formation of the products, and we're going to subtract the sum of the heats of formation of the reactants. So let's apply that formula to this reaction. I want to find the delta H of this particular reaction. I need to take the sum of the heats of formation of the products. So if I look on the table for N2O, it's 81.56. I need to add that to the heat of formation of 3 moles of water. Okay, so when you're taking the sum of the heats of formation, you need to take into account the coefficients. Then we're going to subtract the sum of the heats of formation of the reactants. So we've got 2 NH3, so 2 times negative 46.3. And plus 0, because oxygen is an element already, it's got a heat of formation of 0. Now, as you can see, the actual computation is going to be a bit of a mess, so you need to be careful with the signs, and I would recommend that you double check your calculations when you're doing these. Okay, when you do the math, you get negative 551.24. If you look back at the first example that we did, this is the same reaction, and we get the same value within reason. We're off by about 0.5 for the delta H. So you can see that this formula and using the heats of formation gives us the same value as a longer Hess's law example. Okay. We're going to look further into this though and prove that doing this calculation, so taking the heats of formation of the products and subtracting the heats of formation of the reactants, does give us the delta H for the reaction and is simply an application of Hess's law. We're going to do that by breaking down this reaction into a series of heats of formation reactions. What we're going to do is look at the heats of formation reactions that we can for this reaction. So for NH3, for N2O, and for H2O. Okay, and this is H2O gas that we're dealing with here. So if you take a minute and practice these, okay, which is a good idea, writing out the reactions, okay, with the appropriate fractions. And we get the heats of formation values. So these are the appropriate heats of formation reactions that would apply to this particular overall reaction. Now, if we take these reactions and we apply Hess's law, use these reactions to find the delta H for our goal reaction, let's see what happens. Let's make the decisions here. We want, in our goal reaction, to have 2 NH3 as a reactant. So we would need to take this reaction and we would need to flip it and we would need to multiply by 2. The second reaction doesn't need to change because in our goal reaction here, we've got 1 and 2O. Okay, I've just noticed something here. This should be plus, and this should be an arrow. Okay, so we want 1 mole of N2O. So this reaction doesn't need to be changed. We want in our goal reaction to have 3 H2O. So what that means is that we need to take this reaction and we need to multiply it by 3. Now, if you'd like, you can stop, take these reactions, apply the changes, and ensure that they do in fact add up to this goal reaction. What we're going to look at is not the computation of that because it will work if we do that. We know Hess's law and how it works. What we want to focus on is how these decisions we've made are actually the exact same thing that the formula asked us to do when we took the heats of formation of the products and subtracted the heats of formation of the reactants. Okay. What we did here was we left the 81.56 on its own, and we need to leave the negative 241. The sign remains the same, but we need to multiply that one by 3. Okay. And then this one, the NH3 being a reactant, was the one that we needed to flip, and that caused the sign to change. So anything that is a reactant needs to be subtracted. Okay, and there was no part of oxygen. So what you can see here is that the decisions we made are the same that the formula asked us to do directly. Anything that we wanted to be a product came first and remained the same. It didn't change its sign, but it was multiplied by its coefficient. Anything that was a reactant needed to change its sign, and it was also multiplied by its coefficient. So that shows you that our formula of taking the heats formation of our products and subtracting the heats formation of the reactants is simply an application of Hess's law being applied to the heats formation. You don't need to be able to reproduce this proof, okay, but hopefully it gives you comfort in knowing that this formula, heats formation of products minus reactants, does actually work. What we've done is we've accomplished studying chapter 6, and we've looked at finding delta H in 4 different ways. So we've looked at bond energies, calorimetry, Hess's law, and heats of formation. For calorimetry, we broke out into 2 different types. We had heats of reaction and heats of solution, or heat of dissolving. At this stage, we're going to pause in our topic of thermochemistry and we're going to discuss kinetics. And so it's really important that you apply yourself and do the practice that you need on this topic because it is going to be important later on when we revisit thermochemistry.